All right, good morning. Welcome to class. It is May 4th, so finally made it into May, very last month of the year, well, school year. And we only have a little bit left. We have this week, and then next week is the last week I can give you any new work. So we're getting here right to the end. If you've been keeping up and turning in all your work, I really appreciate that, and I'm glad that you were able to go through and motivate yourself. And that really is something, if you've gone through and done all of your classes, that's something that you should be proud of yourself for. You're definitely going to be set up for like to do the best you can in life. If you're constantly doing things on time, you're going to be giving yourself a lot more opportunities. So even if you look at it and you're kind of frustrated that you did everything on time and then you see people turning in all their work late, just realize, just keep that up. If you keep doing that at every point in life, you're going to set yourself up for the highest possible chance of succeeding and doing really well. um, One thing about grades is I know this grade isn't going to count towards your GPA, but if you just read my announcement, a thing that I hadn't thought about in the past is just the fact that this will probably still show up on your transcript. So when you're applying for colleges, they might just only see your GPA. But imagine you send out your transcript to a college and you see, oh, this student is getting all A's and high B's and they're doing really well and they have a high GPA. And then they get to the online learning portion and they see, oh, low 70s for everything. Just kind of imagine the idea that they would get is they would say, okay, so they're doing really well, and the second they're less accountable, then they do the minimum possible amount of work. So just a thing to kind of think about is this can still show up on your transcripts, and even if it doesn't show up in the GPA, colleges could still easily look at this in order to see how you do, how you compare to everyone. Especially you get to college, it's really independent. A lot of times you're having to teach yourself and you're kind of having to go and figure out a lot of things on your own. So I imagine a university might actually look pretty heavily at how well you worked online and did you do really well? Did it look like you were actually turning in your work and succeeding, or does it look like you're just going to get to college and do the minimum amount possible the second you're not held constantly accountable? So just a thing to think about. If you haven't been turning things in, just please get those in. Even if this doesn't show up on your GPA, it can still really help you or hurt you in colleges. I mean, I imagine it really could. So yeah, there's that. So the other thing is we're going to look at the review now. I'm just going to be answering questions, so I'm not going through the entirety of the review. I just post the answers to it. Your test will be posted on Wednesday, and then we'll just do a little bit of magnetism concepts just because magnets are fun. All right, so the question I got was on number 2 of the review, C, 2C. So let's look at this. We have this circuit right here. We have these two circuits. We have a 9-volt battery connected to the circuits, and the light bulbs have resistances of 50, 75, and 100 ohms. It doesn't label which one is which, but just let's say we have a 50 ohm, 75 ohm, 100 ohm. And it doesn't matter what order we put these in. No matter what order we put the light bulbs in, we're always going to get the same numbers for the math. So if I rearrange all these light bulbs, every single one of those light bulbs is still going to take the same amount of current, still going to get the same voltage drop, still going to have the same power. So it doesn't matter the order we put the light bulbs in our circuit, it's always going to behave identically as long as we still keep putting them all in series or we still keep putting them all in parallel. All right. So it doesn't matter the order, as long as it's not like a combination series parallel and we're not changing it to series or parallel. So 2C is asking about which light bulb is the brightest. So again, when we're talking about brightness, we're really talking about power. So brightness equals power. As long as they're identical light bulb types. Again, if you have different types of light bulb, like a incandescent light bulb, one of those older light bulbs that glows compared to an LED, you can't compare those. But let's say these are all identical light bulbs. So if they're all identical light bulbs, the one with the most power is going to be the brightest. And then that's because power is talking about the amount of energy used per time, right? So if a light bulb uses a lot of energy, it's going to put out a lot of light. If it uses less energy, it puts out less light, as long as they're all identical. So we're really trying to rank the power for all of these. So let's look at our two circuits. So we have circuit 1, everything's in series. We have a 9-volt battery. We go around here. We go through. The light bulb is a circle with an X. You might see this sometimes, or you can just draw it as a normal resistor. Again, doesn't matter which one we put where, but we have a 50 ohm resistor, a 75 ohm resistor, and a 100 ohm resistor. Circuit 2, we have this all in parallel. 9-volt battery. You can also just draw these as resistors, doesn't matter. Just drawing them different ways, kind of showing how you might see these if you look up something or see just a random circuit diagram at some point. 100 ohms. All right, so we have our different power equations, and I like doing this without A or B because it really shows us how we can choose which of these power equations to use. Power is current times voltage. This is the only one I give on the formula chart, but obviously this is open notes, so you can use your notes at any time. But we also have power is current squared times resistance, or power is voltage squared divided by resistance. So when we're looking here, notice we have the resistance of each resistor. So we're probably going to want to use one of our power equations that has resistance in it, right? I know my individual resistances, so I really want one of the equations with resistance in it. So that kind of eliminates this one. I don't want to use current times voltage because I don't necessarily know how much current each object gets or how much voltage each object gets. So here we have series. In series, what do the resistors all get the same where they don't have to share? Is it current or voltage that they don't have to share? So in series, the resistors get the full. So resistors get the full current, get the full current. So they get the full current. That means I probably want the one that combines current and resistance. So for this one, I probably want to use current squared times resistance. They split up the voltages. So because they split up the voltages, I don't want to use the voltage equation. I can go through and I can solve for individual voltages, but it's going to be a little bit harder. And so split up the voltage. So I don't want to use that. Normally, the thing that splits up is going to be harder to use. So over here, we have parallel. What do all of the resistors get the same of in parallel? Resistors get the full voltage. All right, so we know all the resistances. Each resistor gets that full 9 volts. This gets 9 volts, this gets 9 volts, this gets 9 volts. So I don't have to calculate voltage. I don't have to calculate resistance. So it's probably going to be nice to just use power is voltage squared divided by resistance. I would have to calculate each individual current, right? However much current the circuit gets, part goes through here, part goes through here, part goes through here. So I could sit there and calculate all of the currents, but to calculate the current, I'm just going to use a voltage and resistance. So this just cuts out one step. So we also see that we split up the current. So normally, if you can, we're trying to figure out the thing that the objects get the full amount of. Now, for this one, I know each individual resistance, but I don't know the current immediately, so I'm going to have to solve for my total current, which means solving for my total resistance. Now in series, I just add these up, 100 plus 75 plus 50. My total resistance is going to be 225 ohms. And then I can do voltage equals current times resistance, Ohm's law. We're looking at the total for the circuit. So that total current is going to be divide resistance over total voltage divided by total resistance. So the total current here is going to be 9 volts divided by 225 ohms. And we get 0.04 amps. All right, so now I know my current. Each one of these get the same current, so 0.04 amps go through the battery, 0.04 amps go through this light bulb, 0.04 amps go through this light bulb, 0.04 amps go through this light bulb. So I can just use that for all of these. So power through that 50 ohm resistor is going to be the current through the 50 ohm resistor times the resistance of that 50 ohm resistor. So in series, every light bulb gets the full 0.04 amps current. And this is the 50 ohm resistor. And then current squared times resistance. Let's not forget that squared. Power through the 75 ohm resistor is going to be current squared. That gets the full 0.04 amps of current. This has a 75 ohm resistance. And the power through the 100 ohm resistor. And it should be obvious which of these is the biggest, right? Because we have 0.04 squared for all of these times resistance. So we're going to see biggest resistor gets the biggest power or uses the most energy per time. So power for the 50 ohm resistor, power for the 75 ohm resistor, power for that 100 ohm resistor, at least for the series circuit. Go through and calculate those. Like 0.08 watts. This has twice the resistance, so it's going to be 0.16 watts. This is exactly halfway between those, so it's going to be exactly halfway between at 0.12 watts. All right, so far so good. Any questions on why I chose these equations along the way? All right. And I would actually go through and calculate these on your test that's coming up because it's going to be, again, randomized based on your student ID, which means that we can have a lot of interesting things happening. So if I ask which one's the brightest, I would actually go through and solve for each of the individual powers. This one's going to be a little bit easier for circuit 2, right? All of these go from 9 volts to 0 volts, 9 volts, 0 volts, 9 volts, 0 volts. So all of these get full 9 volts. And I know the resistance is, so I don't even have to calculate anything else here. I can just go straight to power through the 50 ohm resistor is going to be, this gets 9 volts squared divided by a 50 ohm resistance. Power through the 75 ohm resistor. Now this should be apparent which one is the biggest now also. Every single one of these is going to be 9 squared divided by the resistance. So we see small resistors are dividing by a smaller number, so I expect a bigger power. So we're going to see the reverse thing happening here. In series, the biggest resistor got the most power, but we're going to see in parallel the biggest resistor is getting the least power. So we're seeing kind of a backwards trend here. By the way, that trend is really hard to see unless you fully take advantage of our different power equations. So power through the 50 ohm resistor in parallel. 81 divided by 50. I'm just going to have to put that in the 1.62 watts. Power through the 75 ohm resistor. And they get different power when we put these in parallel as opposed to when we put them in series. .08 watts, then 0.81 watts. All right. So which one of these is going to be the brightest? What's the actual question? Yeah, which light bulb is the brightest? Yeah, the parallel 50 ohm resistor. And so we can even rank them from brightest to the most dim. And we're going to see the 50 ohm resistor, 75, then 100 ohm resistor in parallel. 50 ohm is brighter than the 75 ohm, is brighter than the 100 ohm resistor, at least in parallel. So we get brightest light bulbs in parallel, and that all has to do with them getting the full voltage drop. And we can also see what's happening in parallel. Again, as I add more resistors in parallel, I get more and more paths. So it gets easier and easier for the current to go through the circuit, less and less resistance. So I get higher and higher currents as I add more parallel resistors. And so we get more and more current with the same voltage, so that battery is putting out more and more power. So parallel is upping our power continuously as we add more resistance, at least for the overall circuit. It's not going to affect the individual resistors. But then we see in series, as I added more resistors, it gets harder and harder for the current to go through because it has to go through more and more individual resistors. So what's the brightest series resistor? Yeah, the 100 ohm. So we see reverse here. The 100 ohm is brighter than the 75, is brighter than the 50 ohm resistor for series. So really bright light bulbs for parallel, not so bright for series. And it's a much more complicated issue whenever we combine a series parallel circuit, though. All right, so parallel tends to be brighter. Parallel, we want smaller resistors are going to be taking up more power, but in series, bigger resistors are going to take more powers. You want to do the challenge? I'm not going to completely do the challenge for you. I can help you along with that. I can give you an idea of where to start. The idea of where to start would be looking at the one before that. Yeah, that's how I normally put this in the calculator. So I just put this all in the calculator all at once. Any questions on C before I move on to a different thing? No questions on C, you're all right. And then D, parallel, is as long as they're identical resistors. So if we have identical resistors, if I put the same resistors in parallel and I put the same resistors in series, the resistors I put in parallel are going to be brighter than the ones I put in series. But I could do different things. Like I could put really big resistors in parallel and really small resistors in series, and I can see different things happening there. Yeah, smallest resistor in parallel is going to be brightest, and biggest resistor in series is going to be brightest. And when you have a series parallel circuit, it's going to be more complicated. A lot of times, if you have a combination series parallel, it's actually going to be the series resistor that gets more of the power, usually, but not always. I mean, I can go through where'd my circuit go? I mean, yeah, we see I have the same going through in series. we go. Yeah, if I put these both in series, we see they tend to be pretty dim. And then if I put these in parallel, they tend to be brighter. They tend to take up more power when I put them in parallel. And then if I put them in a combination series parallel, so let's say it's going to be a little bit trickier to do well. Connect these two. So these two are in parallel now with each other. So these two will be in parallel with each other. And if I put another one here, and then putting that into series, normally we're going to see the one directly in series with the battery is going to take up more of the voltage. And the reason that we can see that happening is these two, when we put these in parallel, the total resistance goes down. So if the total resistance goes down, this is going to take up less of the voltage drop, and this one's going to take up more of the voltage drop. So this is what's normally going to happen. Normally the thing in direct series is going to get more power than the two that are in parallel. But there can be a lot of different things how you could have these with a lot bigger resistances end up taking more power than this one. So yeah, on the test, you're going to want to actually calculate this. So yeah, so on the challenge question, I didn't use the, what do you mean I did use the inverse? Let's look at 3 before I look at the challenge. So number 3, I mean, I want to do like baby steps. I'm like showing you the pool as opposed to just shoving you into the pool. All right, so, or I guess it's not even a pool. It's like throwing you into like a crocodile enclosement. All right, so here we have a battery. We go through these 2 resistors in series, and then we go through these 2 resistors in parallel. So if I were to try to solve for the total resistance or equivalent resistance, just another way of saying total resistance, how would I get the total resistance of this circuit? Am I just going to add up everything all at once? Can I just do this all at once? Like, are they all in series? Are they all in parallel? I mean, it's not a simple series or not a simple parallel circuit, so we're not going to add them all up at once. You probably, there are ways of doing it. Well, I'll get there in a second. But yeah, we're going to be looking at these individually. So I have this resistor here, which is R1 is 10 ohms, and then R2 is 30 ohms. And then we go through down here, and then we go through R3 is 20 ohms, and then R4 is 40 ohms. Yeah. So we have 4 resistors. Which of the resistors are like the others? So which similar resistors do we have out of R1, R2, R3, and R4? These 2 look similar, right? R1 and R2 are in simple series. R3 and R4 are in simple parallel. So to get the total resistance for the series circuits, so resistance total for the series circuit, I just add them. 10 plus 30 equals 40 ohms. Then my parallel, it's 1 over resistance total for the parallel is 1 over 20 ohms plus 1 over, not 30, 40 ohms. which is the same as 2 over 40 plus 1 over 40. So we get 3 over 40 ohms. But I have to flip both of these, right? So I have to do to the negative first power. So we get that total resistance for the parallel part is 40 thirds, which would be 10 times 4 thirds. Well, 4 thirds is 1.333 repeating forever. So we should get 13.33333 repeating forever. So now we combine this circuit, we combine the individual parts, and now we get this individual resistor here. Instead of looking at two in series, I could just say my total resistance of that series part is 40 ohms. But then I could look at my total resistance for this parallel part is that 13.333 ohms. Now, this circuit here, I combine my parallel into one resistor, that equivalent resistance. I combine these series into one right here. So these two combined resistors are in what? Series or parallel? These two are in series. We just add them. So I could just say my total resistance overall is just the sum of those, 40 ohms plus 13.333 ohms, which is how we get 53.333 ohms is our total resistance for this entire circuit. So we had to go through and split these up individually. Now, I'm a little bit lazy, so instead of doing that, how I might do this is I just see these are in series, so I add them. So I just do 10 plus 30 plus, and then these are in parallel with each other, but that parallel branch is in series with this. We see that because when I combine these two together, I get this resistor here. This is in series with this, and so I could just do add up the inverses. So 20 inverse plus 40 inverse inverse, which is how I would do that. And that's how we're getting something similar to how I wrote that bonus answer. See how these are equivalent statements? So this is what I would normally do. I don't suggest that you all just go through and do this because that's really easy to mess up. It's probably better if you just kind of go through and slowly collapse down your resistor. So then I could look at this challenge circuit that looks like this. Fun, right? I like it. It's actually nowhere near as bad as it gets. It actually gets way worse than this, where you don't even have simple series and parallel, and then you just have to create systems of equations to solve for it. And so you can get to the point where you're having to solve like a system of 10 or 20 different equations. Um, and honestly, that's how complex circuits work. And you have down to say the like processor in your computer can have literally billions of transistors. In fact, if you have a more modern, if your computer isn't like over a decade old, you probably have several billion transistors in the PCU itself. So if you wanted to actually solve that, you would have like a system of billions of equations you would actually have to solve, which even for a computer would take a really long time to solve, which is kind of cool that you could solve for the circuit inside your computer using the computer. That's still weird to me. It's kind of like how we can use our brain to describe our brain and possibly potentially at one point create a new brain. It's just weird to think about. You're using your brain to think about your brain. All right, so we're trying to find the equivalent resistance here. I'm going to draw this out. 100 ohms. Then we go through down this way. 25 ohms. 75 ohms. Then we go through here. We have 50 ohms. Then we have this one, which is 80 ohms. Then we go through 40 ohms. Then we go through 20 ohms. So when we do this, we can't do everything all at once. We need to kind of look at this and find the parts that are similar. So where on this circuit do we have things that are in nice simple series or nice simple parallel? So we have R1 through R7. We don't have any that are in nice simple parallel yet. None of these are in nice simple parallel. We have 2 sets of resistor in nice simple series though. Well, this 40 ohm and 20 ohm resistor are in a nice simple series. And this 25 and 75 ohm resistor are a nice simple series. So I could add those up, right? In series, I just add up the 2 resistances. So again, it's probably best to go through and redraw our circuit each time we do this. 25 plus 75 is just a 100 ohm resistor right there. Combine those. Still have this 50 ohm resistor, this 80 ohm resistor. And now I combine these two, 40 and 20, so that's pretty much like a single 20 ohm resistor. Now I have not 20, 20 plus 40 is 60. All right, now I have a simple parallel spot I can look at. So where's my simple parallel? It's at the very end. This 100 is not in simple parallel. The thing keeping this in simple parallel is I have to go through this 50 ohm resistor. If there's a thing in my way that's not parallel, that messes me up. This 80 and 60 ohm are in simple parallel, but then I have to go kind of through series to get to this 50 ohm resistor to here. But then this is in parallel with this. And so it's not a simple parallel circuit. Let's imagine I just have this circuit here. It would be series, then parallel. The only 2 resistors that are in simple parallel are these 2 resistors. So normally we're starting from the end and going in, and sometimes it helps put your hand over this and it makes it more obvious series than parallel. And so if I trace backwards, that means these 3 aren't in simple parallel because I have to go through this one in series to get to the other 2 in parallel. So that means I need to look at these 2. Normally, we're only going to be looking at 2 at a time. And when you have a circuit that's more complicated like this, you want to start at the outside and go in. But now we have a simple parallel here. And then, so the total resistance there is going to be the sum of the inverses. So 80 inverse plus 60 inverse, but we need to inverse this whole thing, right? Because it's 1 over resistance is 1 over plus 1 over. So 1 over plus 1 over, and then I have to do 1 over that whole thing. Inverse. So we get 34.286 ohms. So now I can redraw my circuit. Now I have a 100 ohm resistor here, a 100 ohm resistor here. I still have this 50 ohm resistor that was causing us difficulty earlier, but now these 2 combine together, and again, in parallel, the total resistance is smaller than the sum, so I have an 80 and a 60 ohm resistors, I get a resistance that's smaller than my smallest resistor. So I get 34 point, I'm just going to round that to 29 ohms. I'm even going to be lazy here. You can round that to 34.3 ohms. You normally don't want to round this much in an intermediate step. All right, now I've collapsed that down. Now this 34.3 ohm resistor, what is it in with another resistor? Simple series or a simple parallel? Simple series with a 50 ohm resistor, right? So now we see here, we're in simple series. There's a reason why this was a challenge. So now I can just add these two together. So my total resistance is just going to be the sum of those, which is going to be 84.3 ohms. So now I get here, now I have a 100 ohm resistor. Now this goes down to a 100 ohm resistor here. But now these two resistors I combine together into a single resistor, a single 84.3 ohm resistor. Now, is this in simple parallel or in simple series? Parallel. So now I can combine these two together in parallel, and then I'll get a total resistance there, and then I could collapse that down, and then I could get here, it would go around to the 100 ohm resistor, and then down to the 100 ohm resistor, and then, but I would combine that together, and so it'd be a total resistor. And then now, whenever I do my total resistance of these two, we have a simple series, and I can just add those. So we're slowly having to step this circuit down. Or, if you want to see what I really did there, is when I went through and did this, I saw, oh, these two are in series. So I could do 20 plus 40 right there. Those are in series. But then that series is in parallel with this one. So I need to do the inverse of it. So the inverse of 60 plus the inverse of this one plus 80 inverse. But then I need to invert that whole thing. All right, so now I have these three resistors combined. But now we're in simple series with this 50 ohm resistor, so I just added 50 right here. Okay, but this whole thing together, 50 ohm resistor, is in, so this is all four of these are in parallel with these two. So I need to do -1 of this plus that these two are in series. So I just add those 25 plus 75. But I need to do this whole thing inverted plus this whole thing inverted. And then I have to invert the entire thing. So now I'm switch this back, but now this single resistor here is in series with this, so I can just simply add 100 to that. And that's how I got that weird looking expression there, instead of going through each of those steps. But again, I don't expect you to be able to do that. Obviously, I've been doing circuits for, again, it's literally over half my life now. You can if you're really careful, and you like, again, I've looked at circuits for a really long time, so I'm pretty good at it. I wouldn't expect any of you to be able to do this perfectly just like this. And part of the reason I just wrote that like that on my key is because you're going to have a bonus question like this on your test, and I didn't want to just directly tell you every single individual thing to go there. But yeah, I would suggest stepping it down like this and going through each steps. Then yeah, you also have to be really careful when you do these that your parentheses line up really well. I will grade your mock exam if you turn it in, yes. And I'll give you a 1 through a 5. Any other questions on here? That's those are honestly the parts where I expected y'all to have trouble with. Yeah, the power question was really good. Series parallel, being able to find that. The challenge question, obviously, that's much harder than anything we've ever done, which is why it's a challenge, and your bonus is also going to be a similar difficulty. If there's no other specific questions about the review, then I'll stop the video here. If you still have questions about the review next class I'll put the test up on Google Classroom, and I can help you with the review there also. Let's see, 2E. Another light bulb is added to the circuit. Okay, there we go. That's another really good question. So, added in the same way as the other ones. So we have circuit 1, which is that series circuit. We have a battery. We go through each resistor. Then we have circuit 2, and we're looking at 2E right now. Battery goes through like this. Then we have all these parallel resistors. All right, so the hardest question I gave you was something with, I gave you not enough information. Yeah, those, sometimes I accidentally don't give you enough information. That does happen. Or sometimes I actually accidentally give an unsolvable question. But even getting to the point where you can prove it's unsolvable, I actually consider that good. All right, so E, we're talking about we're adding a resistor in the same way as before. So I add in a resistor to 1. So let's say I put that resistor here. So I add in a resistor. That. But here, number 2, I add in a resistor in the same way. So I add a resistor in parallel. So this is my added resistor. So looking at these, again, back to way back here when we figured out what equation to use for each. So for in the series circuit, I wanted to use power is current squared times resistance for each resistor because they all get the same current. But for this circuit, I wanted to use power is voltage squared divided by resistance because they all get that full 9 volts. So, and then notice I didn't say the size of the light bulb. It actually doesn't end up mattering. So when I add in another resistor, my total resistance changes, right? For both of these, my total resistance change, but my individual resistances don't change, right? So light bulb keep the same resistance. So all of the little R values I'm using here, because I'm looking for which light bulbs get brighter, which light bulbs get dimmer. So all of the individual resistances stay the same for each individual light bulb. Our total resistance changes, but each individual resistance does not. All right, this is an important distinction here. So the light bulbs keep the same resistance. So let's look at this. When I add a resistor in the series circuit, what happens to my resistance? Is it harder or easier to go to this through the circuit? So I had to go through 3 lines. Now I have to go through all 4 lines. So it's going to get harder to go through here. So my total resistance goes up. So each light bulb kept the same resistance, but for my entire circuit, I have a bigger resistance now. I have to go through, instead of all 3 light bulbs, I have to go through all 3 light bulbs and a 4th light bulb. So it's harder to go through. Total resistance goes up. So total current goes down. Well, I see here that for my series circuit, I'm using power is current squared times resistance. For each light bulb, they get that total current, right? Power through each bulb. They're in series. They each get that total light bulb times the resistance for the bulb. Now my total resistance changed, but my individual resistances did not. My total resistance for the circuit went down, so my total current going through each light bulb went down. So what happens to the power of each light bulb in series? Well, they all get less current. They all keep the same individual resistance. So they all get less power. So all the series bulbs get more dim. Right? So as they keep adding and adding in more in series, they get more and more dim. One way of looking at it is we get more and more resistance, less and less current. Or I could also look at them as in series, we have to share the voltage. So as I keep adding more and more light bulbs in series, they have to share the voltage between more and more resistors. So this 9-volt battery, if I keep adding these, they keep splitting up that 9-volt into smaller and smaller voltages. They keep getting less and less, and so they get more and more dim. But let's look at it parallel. Parallel is interesting. In parallel, we're going to want to use this power equation as voltage squared over resistance. So this is 9 volts, so I go from 9 volts down to 0 volts. When I add this other resistor, what happens to the voltage drop? So the resistors are unchanged. Each one still gets 9 volt. So they all still get 9 volts. Each resistor is the same, right? Because I'm talking about the resistance for each light bulb, not total resistance here. They all get the total voltage, but we're talking about the resistance for each light bulb here because we're talking about the power for each light bulb here. So they all get the same voltage. They all have the same resistance. So all parallel bulbs stay the same brightness. And this is, again, why you can have a TV on, you turn a light on, you start using a microwave, your TV doesn't get more and more dim as we're plugging more things in parallel. They all keep getting that full 120 volts from the electrical outlet. The resistance of the object itself doesn't change. So everything stays the same brightness. Everything keeps drawing the same power. So none of these actually get brighter. So none of the bulbs get brighter. And then in parallel, there are quite a bit more things going on here, right? Because we see as we add resistors in parallel, it gets easier to go through the circuit, right? I could go through 1, 2, or 3. If I add a fourth resistor, I could go through 1 or 2 or 3 or 4, right? Again, it's a grocery store opening up more checkout lines. It gets easier and easier to go through. So as I add resistors in parallel, we see our total resistance actually goes down. So our total current goes up. So we have smaller and smaller resistance, so our total current goes up. So we added another path here. So I have to split current goes through 1, some goes through 2, some goes through 3, some goes through 4. These have to split up and share all of that current. But because my total resistance went down, my total current goes up. So that means even though these are all sharing, my total current goes up in the exact amount that this new branch needed, which is really cool in my opinion. So these keep getting the same current. I end up needing more current. When I plug this in, it adds just enough current to exactly add the exact amount of current that this needs. I add another one in, all of these will still get the same current, and then my total current goes up just to add enough current to go through here. So as you keep adding devices in, your total current goes up through a circuit, but each resistor keeps the same voltage and resistance, so they keep drawing the exact same currents. They keep drawing the same power, but the total power goes up by just enough in order to add the next one. But this is also what starts getting dangerous. If you plug too many things into an outlet, eventually the amount of current you draw through your house keeps going up and up and up. Eventually, you get to a point where a circuit breaker has a limit on the amount of current that goes through, and it'll trip. It'll open up the circuit and stop current going through before it's so much current and so much power that it gets too hot and starts fires. So that is a drawback in parallel. But this is, I mean, that's really neat to me. You just keep adding things in and they keep getting the same power, and your circuit just adds the exact amount of extra current it needs to add more to go through that new path. Is that making sense, or is that still confusing? Because it's tricky, the difference talking about individual resistors or the entire circuit itself. And this is a spot where I expect a lot of difficulty because there's a lot of subtleties to it. Makes sense. All right, that's good. Because I was about to say, if it doesn't make sense to you, the average person in the class is not going to do well. All right. So yeah, that's most of it. Those are kind of the more difficult things, places I expected people to have questions. So I just post the answers. Again, keep going through that. If you have more questions, Wednesday I'm going to post the test, and I'm just going to go through like I've done for every other one, just practice setting up the questions because it's randomized in a very similar way to the previous ones. So we'll go through how to do that. And if you have any more questions on the review as you go through, you're getting a different answer, you can ask them then, or you can email me a question, anything like that. Other than that, have a good day. Good luck on the review, and feel free to stick around and keep asking questions.